Hello and welcome to another Math 4 Honors lesson. I'm Kirk Weiler, and today we'll be looking at Unit number 6, Lesson number 1 on periodic functions. Throughout this entire lesson, I'm going to assume that you've already had a course in Algebra 2 with trigonometry, meaning that you've already had all of the basic work with trig, including sinusoidal modeling. So most of the terminology, and in fact most of the information in this lesson, is thought of as being review. If you haven't already had a significant amount of trigonometry, most likely this lesson is not developmentally appropriate for you, and you might want to find one that is. But let's take a look. The first thing that we want to understand when we talk about periodic functions are what periodic functions are. So let's understand the definition of a periodic function. A periodic function is one whose outputs repeat at regular input intervals. There are examples of periodic functions all over the place, especially when you think about the natural world. If you think about the way that tides rise and fall, well, the depth of the ocean, let's say at a beach, is definitely periodic because it keeps repeating the same pattern over and over again. Likewise, if you think about the number of hours of daylight there are in a given day, that is definitely periodic, right? And it repeats itself once every year. All right. There are many, many other examples that range from acoustics to electricity to all sorts of things. But let's get into the first exercise. All right. In the first exercise, what we want to do is just get a feeling for a particular periodic function. And one of the great things in the real world that gives us a lot of opportunities to discuss this, believe it or not, are Ferris wheels. Because when you're on a Ferris wheel, your height on the Ferris wheel keeps repeating itself. So that's what we've got going on in exercise 1. We've got a Ferris wheel with a radius of 35 feet. A person gets on at t equals 0 at the lowest point, which they tell us is 5 feet above the ground. A complete rotation of the Ferris wheel takes 4 minutes. So in letter A, we're asked to sketch a graph of 2 full rotations of the person's height as compared to time. Pause the video now if you think you know how to do this and make an attempt at sketching this graph. All right, let's take a look at the graph. Really nice graph, even if, whoa, I don't know what happened there. Let's get the pen active. There we go. All right. You got a little glimpse of the next problem. Anyway, let's take a look at this. We want to graph the height of the person over time. And what do we know? We know at t equals 0, the person is 5 feet above the ground. And we know that every 4 minutes, the person returns to 5 feet above the ground. So those 3 points are definitely on our graph. Now, let's understand the way a Ferris wheel looks. We've got a Ferris wheel, and we know that the person gets on at the bottom, and that's 5 feet from the ground. Obviously, since it takes 4 minutes to complete a full rotation, after 2 minutes we're going to be at the top of this Ferris wheel, assuming sort of constant motion. Where are we? Were you able to figure this out? If not, pause the video for a minute to see if you can figure out where we are at 2 minutes. All right, hopefully you figured out that we were 75 feet above the ground. And of course, the reason for that is that although the radius of our Ferris wheel is 35 feet, the diameter is 70. So we've got the 5 feet plus the 70 feet, and that puts us at a height of 75 feet at 2 minutes, and of course, at 6 minutes. How we connect these is not obvious, but we're going to do it with a nice smooth curve. This is a lot harder than it looks when you're writing on a pad, but there we go. That is roughly the way our graph looks. Letter B, what we're going to do is we're going to review some terminology associated with periodic functions. I'd like to find now this function's amplitude, its midline, and its period. If you think you remember what these terms mean, pause the video now and see if you can find each one. As an aside, each one of these actually has units, so try to think about what the units are as well. Pause the video now. All right, let's go through them. Amplitude, midline, and period. Amplitude. Amplitude is how far above and below the midline the phenomenon goes. So let's actually draw the midline. I like to draw it in dashed. All right, this is the midline. The amplitude, on the other hand, is this thing. I'm going to just abbreviate as amp, if that's okay. All right, so we want to figure out the midline. We want to figure out the amplitude. I'm going to actually figure them out in that order. So I'm going to do the midline first. I know I asked them in the opposite order, but I'm going to do this one first. The thing I love about the midline is it's always halfway through the peak y value and the low y value, halfway between, I mean. Now, a number that is halfway between two other numbers is, by definition, the average of those two numbers. So I can always figure out the midline by averaging the peak y value and the lowest y value. Here we'll get 80 divided by 2, and that will give me 40. And I really want you to understand that's an equation, y equals 40. Whoops, y equals 40, not y equals 50. Y equals 40, and specifically y equals 40 feet. Let's figure out the amplitude. The amplitude is how great of a distance you go above and below the midline, above the midline and below the midline. This is pretty easy to do. You can do it in a variety of ways now that you know the midline. You could do the maximum minus the midline. That'd be 75 minus 40, 35. You could do the midline minus the minimum. 40 minus 5 gives us 35. One thing that I would like my students to know, so if you're one of my students in Math 4 Honors, please make sure to understand that you can always find the amplitude by taking the peak y value, subtracting the lowest y value, and again dividing by 2. It's going to give me 70 divided by 2, or 35, and again, feet. Now, I want to make sure that you understand why we can do that. When we subtract two numbers, we always find the distance between those two numbers. So when I subtract that 5 from that 75, what I'm finding is I'm finding this vertical distance. All right? And then, of course, the amplitude is simply going to be half of that. So I really would like my students to know that physical interpretation of amplitude. Okay, but let's now get into the period. The period is very different than the midline and the amplitude because it has to do with the x or the t values, not with the y values. Specifically, the period is the distance along the horizontal axis that it takes for the phenomenon to repeat itself. Now, in this particular case, what's beautiful about the period is it has a nice physical meaning. The period in this case is 4 minutes. It takes 4 minutes for us to complete the rotation. Now, if it's not obvious, I'm going to do it in a different color. I'm going to go with green. You can also track the period length by, let's say, measuring the distance between two consecutive maximums or two consecutive minimums. All right, that's one nice way to do it. Okay, so I'm going to leave the text up just for a moment, then I'm going to scrub it out so I can go to the next exercise and have a place for my head to be. All right, let's go on. Let's scrub out the text. Bye-bye. And let's take a look at exercise number 2. In exercise 2, we're given the graph of a periodic function, and what we want to do is come up with its amplitude, its midline, and its period. Now, I don't want you to worry whatsoever about the actual equation. I know you've done sinusoidal modeling before. We'll get to that in the next lesson. Actually, it's not the next lesson, but the one after that. Anyhow, not the point. The point is we just want to come up with that amplitude, midline, and period. Pause the video now, take as much time as you need, and see if you can figure it out for exercise number 2. All right, let's go through it. You can do these in any order you want. Let's take a look at the information that we're given. Right here, we know that we've got the point 0, 12. And please note that it's a max. Right, then we have the point 3.2, comma 6. I started to write the word min a little bit too quickly, and it's a minimum. All right, what's nice is if I know the maximum y value and the minimum y value, I can get the amplitude and I can get the midline very quickly. Let me do the midline. Please note, again, the midline always has an equation, not midline equals, but y equals, or f of x equals, or something. Again, for me, the easiest way of always visualizing the midline is it's the average of the peak y value and the lowest y value. So my midline here is y equals 9. My amplitude, again, many different ways of doing this now. Amplitude, it's literally amplitude equals. You could do the peak value minus the midline. You could do the midline minus the minimum. You could do my method, which is to take the peak value, subtract off the smallest value. That gives you the vertical separation between the two, and then divide by 2. Any way you go about doing it, you find that the amplitude here is 3. There's no units attached in this problem because there's no units that are given. Now let's talk about the period. That might be the hardest thing because some students might look at this and say, well, the period is 3.2. But keep in mind that if we measure the distance from here to here, the horizontal distance, which is most certainly 3.2, that's only half a period. What we need to have is we need to have the entire distance, right? This is going to be our period. So what we're going to do now, obviously, is we're going to just double. In this case, the period is just going to be double that 3.2. We have a period of 6.4. So that's something that you definitely want to be able to do quickly and accurately. If you're given sufficient information on a periodic graph, sufficient, because we could have been given other points that would have made this very difficult. But if we're given sufficient information, like especially information about maximums and minimums, we should be able to come up with the equation. All right, again, let me pause just for a moment so you can look at the text on the screen. All right, I'm going to scrub. All right, now I'm scrubbed. Let's go on to the next page. All right, now we're going to get into the two most important periodic functions that have ever been invented, the sine function and the cosine function. Now again, going back to the idea that you've had some pre-calculus, some trigonometry in Algebra 2, the way that we define the sine and the cosine function, the definition, it's just what we've decided, is that if we have an xy point that lies on the unit circle, remember the unit circle is a circle with a radius of 1, and theta is the angle measured counterclockwise from the positive x-axis, right? So this is the positive x-axis, theta is measured positive counterclockwise. Then we define the sine and the cosine as simply cosine being x and sine being y. Again, let me make sure that you understand why this works, right? We want this definition to be consistent with our definitions from right triangle trig. So what we do is we've got this right triangle, right? And of course this length is simply the x-coordinate. This length is simply the y-coordinate, and the radius is 1. And we know from right triangle trig that we always want the sine of the angle to be the opposite divided by the hypotenuse. But on the unit circle, the opposite is the y-coordinate, the hypotenuse is 1, so the sine is simply the y-coordinate. The cosine, likewise, from right triangle trig, we want it to be the adjacent side divided by the hypotenuse, which is going to be x divided by 1, or the x-coordinate, right? So what's really nice about this is it allows us to take right triangle trig and extend it to angles that are positive, negative, greater than 90, right? We can now figure out the sine and the cosine of any angle by simply orienting ourselves on the unit circle and finding the point that we end up with given an angle. Now, all that makes a lot of sense to me because I've been dealing with the sine and the cosine since the mid-1980s. Michael Jackson was still around at that point. So was Ronald Reagan and the Cold War and all that good stuff. Sine and cosine take a long time to get used to because they're the first type of function that you really deal with that's non-algebraic. You can't really think of sine and cosine in terms of, oh, multiplying and dividing and exponentiating. You just can't do it, right? But let's use these definitions, very important. Cosine is the x-coordinate on the unit circle, sine is the y-coordinate, and let's solve some problems. I'm going to scrub. Ready? Scrubbed. All right, next page. So take a look at exercise 3. It says determine each of the following values by using the definition of sine and cosine. So sine and cosine's definition almost becomes a table of values for us. Now let's take a look at the angles that we have. We've got the sine of 90, the cosine of 270, and the cosine of negative 180 degrees, all degrees. If you're wondering why we're not working in radians today, it's because in the next unit in the next lesson, we're going to review what a radian is and why it's important. All right, so all degrees today. Okay, anyway, you don't want to do this with your calculator. Pause the video and see if by using the definition of sine and cosine alone, you can come up with these three values. All right, let's go through it. Let's take a look at sine. What I would want to do to figure this out, and eventually we definitely want to be able to do this in our head, is I would sketch the unit circle and I would locate where 90 degrees is. Well, it's very important to note that that's 0 degrees. So 90 degrees counterclockwise is going to be at the top of the circle. I know that the sine function always returns the y-coordinate on the unit circle. And hopefully what's obvious is at the top of the unit circle, the y-coordinate is 1. Now you should check yourself right now. You should take your calculator, type in sine of 90 and see if you get 1. Clearly your calculator has to be in what's known as degree mode right now. You need to tell the calculator what language you're speaking in. We're speaking in degrees. So check your answer. All right, hopefully you got 1. Let's take a look at cosine of 270. Same idea, slightly bigger diagram. Thought that first one was a little bit too small. All right, the question is, where's 270? Well, here I'm at 90, here I'm at 180. 270, right? 270 degrees, I am at the bottom of the circle. Here I am with coordinates what? 0, -1. So I know that the cosine of 270, that doesn't look like a 2, is equal to the x-coordinate at that point, but that's just 0. So cosine 270 is 0. All right, let's take a look at the cosine of 180 degrees. Oh, I'm sorry, -180. Angles, in a certain sense, are almost like vectors in that they tell you both how much to rotate and in what direction. So here I'm at 0, sure, but here I'd be at -90, and all the way over here I'd be at -180. So I'd be right here. That's got coordinates of -1, 0, and the cosine is always the x-coordinate, so it's equal to -1. All right. There are certain values of sine and cosine that you want to be able to do very, very quickly and in your head. The quadrantal angles, the angles that are multiples of 90, are integer multiples of 90, sorry, are definitely some of those angles. In future lessons, we'll also talk about things like integer multiples of 30, 45, and 60, but I don't want you to worry about any √2/2 or √3/2 or anything like that right now. All right? I'm going to pause the video again before I scrub the text. All right, scrubbing. Here we go. Let's take a look at exercise number 4. It tells us that a point is located on the unit circle at an angle of 118 degrees, and it asks us to determine the coordinates of the point to the nearest hundredth. If you think you know how to do this with all the technology that you own, please pause the video and make an attempt. What's interesting about this problem is that it sort of turns the definition of sine and cosine on its head, right? Because what we're going to do is we're going to use this definition to come up with the coordinates as opposed to the last problem where we use the coordinates to actually come up with sine and cosine. This is quite possibly one of the worst circles I've ever drawn. I'm going to get better at it, I promise, on this tablet. But here's my quote-unquote unit circle. Let me at least put 1 and 1 on it. And what I know is I'm at an angle of 118 degrees. So maybe I'll just sketch that on. Maybe this is a rotation by 118 degrees. And what I need to know are the x and the y coordinate pair. Well, the plain fact is that the x is simply going to be the cosine of 118 degrees. So I'm going to take my calculator out. I'm going to punch that in. It's going to be kind of ugly. But if I round it to the nearest hundredth, it ends up being -0.47. I like the fact that it's negative, right? Because I'm in the second quadrant. The x-coordinate is definitely negative in the second quadrant. The y-coordinate will be the sine of 118 degrees, which again, to the nearest hundredth, is 0.88. And again, I like the fact that the y-coordinate's positive, because in the second quadrant, y is positive. So that's it. Just reinforcing the idea that the x-coordinate gives you the cosine, and likewise, the cosine gives you the x-coordinate, and same idea with sine. Again, I'm going to scrub, take a moment. Scrubbed. All right, let's move on to the next sheet. Now, we'd also like to be able to extend the sine and the cosine ratio to circles that have any radius. This is extremely important. Don't brush it off. This will actually form the basis of a lot of work that we'll later on do in what's known as polar coordinates. So let's take a look at the development. It's all in the box there, but let's see how it goes. Let's now take a look at a circle with a radius of r centered at the origin, same angle theta. Right, but now of course the deal is the radius is r. This is still the x-coordinate. Oh, this is not accurate anymore. I'm sorry, let me just cross that out. I apologize, bad graphic there. That's the x-coordinate, that's the y-coordinate. Maybe we'll come back and we'll actually modify that to be what it should be. Right now, of course, what I'd know, based on right triangle trig, is that the cosine of theta will be the x-coordinate divided by r, right? So that's now this formula. Oftentimes, what we're going to want to know, though, is that the x-coordinate is the radius times the cosine of theta. Likewise, we can do the same for sine. The sine of the angle is equal to the y-coordinate divided by the hypotenuse, right? So that's this relationship. And then we can rearrange that. The y-coordinate will always be the radius times the sine of the angle. I really want to pause just for a minute and emphasize how really important this is. I look at the cosine and the sine theta, the cosine and the sine functions almost as like, they're not percents, but they're definitely ratios. And what they do is they sort of divvy out the radius. I know that seems weird, but as the radius sort of swings around the circle, what happens is that a portion of the radius, sort of, if you will, lies in the horizontal direction, a portion, a fraction of it, and a portion of the radius lies in the y direction. The fraction, if you will, that lies in the x direction is always given by the cosine, and the fraction that lies in the y direction is always given by the sine, assuming, and this is a big assumption, that theta is measured counterclockwise from the x-axis. All right, so in fact, the way this should have looked is r cosine theta, r sine theta. Sometimes errors aren't so bad because they give us a chance to discuss them. So pause for a minute, really think about that development. I can't tell you how important it is. Really, this is really quite critical. If I ever want to know the horizontal component, I'll take the radius and figure out how much is in the x direction. Likewise, the radius, figure out how much is in the y direction. Do you have all of that? All right, it's gone. Let's take a look at the last few problems in this lesson. Number 5 tells us that we have a point located on a circle whose radius is 8. So we are no longer working with the unit circle, and that's important. It's at an angle of 210 degrees. We want to determine its x and y coordinates and round, if needed, to the nearest tenth. All right, pause the video now and see if you can do this problem based on what we just spoke about. All right, let's do it. So you can just memorize those formulas, you really can, but let me make sure that we can kind of visualize them, right? We've now got this circle, 210 degrees, that kind of puts me down in the third quadrant because it's bigger than 180 but less than 270. So 210 degrees. I know that this length is 8 and I need this xy pair. It's probably a lot harder to see the right triangle trig once that angle gets larger than 90. That's why it's great to just have these formulas. The x-coordinate will always be the radius times the cosine of the angle, and the y-coordinate will always be the radius times the sine of the angle. Literally, it's like the radius is the whole, right? It's the whole thing. It's as big as x and y could possibly get. The question is, how much of it lies in the horizontal and how much of it lies in the vertical? So if we simply take 8 times the cosine of 210 degrees and 8 times the sine of 210 degrees, we're going to get those two coordinates. To the nearest tenth, they're going to be negative 6.9 in the x. Yep. Oh, and a beautiful negative 4 in the y. I guess to the nearest tenth, negative 4.0, but that is an exact answer. All right. Easy. Make sure to know them, especially if you're one of my students. X equals r cosine theta, y equals r sine theta, as long as the circle is centered at the origin and as long as the angle is measured in the positive counterclockwise direction from the positive x-axis. That's a lot. Let's take a look at exercise 6. I'm going to scrub out number 5. Or I'm going to try, oh my goodness, it's just like everything just got wacky. All right, hopefully that got me back on task. Don't ever touch the Mac while you're doing this. All right, let's take a look at exercise number 6. We've got a Ferris wheel. Back to our Ferris wheel, right back where we started. Its center is 73 feet above the ground. Got it? Center is 73 feet above the ground. The diameter of the Ferris wheel is 130 feet, the diameter. If theta represents the counterclockwise angle measured from the 3 o'clock position, then determine a function that models the height of the person above the ground as a function of theta. Not as a function of time, but as a function of the angle. So pause the video for a moment and see if you can come up with this function. I want a function that as its output gives me the height, and the input gives me the angle from that 3 o'clock position, right? You may want to draw a picture. Pause the video now and think about it for a little bit. All right, let's go through it. I'm going to try to visualize it a bit. You know, I've got this Ferris wheel. What do I know? That's my ground. Then I know that the center is 73 feet above the ground. All right, I'm going to pop this out for a second. Forget about the 73. Just don't even worry about it. Don't even worry about it. This is that 3 o'clock position. You'll hear me refer to that a bit as the course goes on. The 3 o'clock position, I'll sometimes call it due east. I'll call it the positive x-axis. We know that the diameter is 130 feet, but what we really need is the radius, right? The radius is 130 divided by 2, or 65 feet. So let's just say that we have this theta. One thing that I would know is that this coordinate point was what? 65 times cosine of theta, and 65 times sine theta. Now a lot of students just want to say, well then I have it. There it is. 65 times sine theta. The problem is that's not correct. That 65 times sine theta, I'm going to go in a different color so you really see it, is this distance. So that 65 times sine theta is simply the distance from that 3 o'clock horizontal position up to our point. In fact, if I want the height above the ground, I then also have to add in that 73 feet. All right, that 73 feet is never going to change. You're either going to be adding a portion of the 65 to it or subtracting a portion of the 65 from it. So we can now say that our final function, h of theta, and I like to look at it like this. It's going to be 73, that's a nice 3, isn't it? Plus 65 times the sine of theta. Again, that's a 3. That's a better 3. But that's it. All right, I know that last one can be tricky for students because they get kind of keyed in on this r sine theta, so they think that's the answer. But that's always the vertical distance from the center of the circle. If the center of the circle isn't located at 0, 0, you have to adjust for that. Hope that makes sense. All right, I'm going to scrub out the text one more time, and I think bounce the screen around a little bit more, make you some more seasick. And let's finish up. All right. I want to thank you for joining me today for Unit number 6, Lesson number 1 on periodic functions. This has been Math 4 Honors, and I'm Kirk Weiler. And until next time, keep thinking and keep solving problems.